Hello, I'm going to give a talk today on elf loading. It's going to be a hopefully deep enough dive for you into runtime linking, so we'll see how that goes. A little bit about me before we get started. I got my bachelor's at Northeastern in 2018, spent 5 years in defense. Since about 2019, I've been working on FOSS in my free time. Two main projects, SerenityOS and the Ladybird browser, which, if you're familiar with those, are very closely related projects. I have been working full-time, like as a paid position on the Ladybird browser since August of last year. And I currently work for the Ladybird Browser Initiative, which is a 501c3 profit registered in California as of July or so, though their official tax status is pending. So, but my opinions are my own. I don't represent the nonprofit here at the moment, of course, but if you're interested in that, come talk to me at the pub afterwards or visit ladybird.org. One other thing to plug here before we get started is we are running a browser jam the weekend before CPPCon. So if you want to do a game jam, but instead of building a game, you're going to build a HTML parser, check out that on our GitHub, or on this GitHub, which is not related to the nonprofit. Anyway, okay, so what's the plan today? We're going to talk about compile time linking before we talk about runtime linking, because you kind of have to understand what linking is before we can talk about dynamic linking. We'll talk about the role of the loader in runtime linking. Then I'm going to do a little demo code tour of how this all works in the SerenityOS code base. I'm going to whip out CLion and start scrolling through code. Hopefully that's what you guys were hoping for. Deep dive might be a little aggressive for the slides part, but hopefully the code tour helps scratch that itch. Okay, so first, we have to talk about linking in general. So hopefully you're familiar with this diagram here of how the C++ compilation, or C and C++ compilation process works. Right, your source files go into the compiler, which goes into the assembler. For each source file, you generate a bunch of object files, and then the linker gets invoked to do something, and eventually you get an executable. So we're going to go over what that something is today and how that works for both the compile time link part and the runtime link part and loading part. So some terminology here. I believe I pulled these two terms from the Oracle reference that I have at the end of the slides that I'll link in the Discord later. But the link editor here is your standard compile time linker that you think of when you think of linking as a developer writing C++. So this application, its job is to take all the object files and turn them into an executable or a shared library. The second piece is the runtime linker. This is responsible for, as you might guess, runtime linking. It's also generally the same program as the loader, or the runtime loader in most ELF systems. So what this does is it takes your executable and it loads it into memory. So it takes the file contents, puts them into memory, and allows you to execute. It's also responsible for managing shared library dependencies, loading those into memory, and thread local storage, which I'm not going to talk about today. So basic flow, we have source files that go to the compiler to the link editor, where this link editor is going to be the GNU linker, BFD. It's going to be the LLVM linker, LLD. Might be the Microsoft linkers, but not for ELF. It could be the mold linker, whatever else. And then after we got our files on disk, your executable and shared libraries are going to be passed through the runtime linker, generally called lt.so, to actually execute in memory. So that's types link. Okay, so let's go over a bit of compile time linking for ELF files here. So the output of the compiler is going to be this object file. The most important part of ELF which is the executable and loadable format, linkable format, whichever L you want. But the most important part is all of the sections. So at the top of the ELF file, there's a table of section headers, and each of these sections does something interesting when you start trying to either link a bunch of object files together or execute those files at runtime. The most important ones are the ones that I've listed here, which is .text, which is going to be your executable code, where text means code, not strings. There's no ASCII strings in there. It's all machine code. You've got your data section, which is global data. You've got ESS, which is zero initialized global data. You've got RO data, which is read-only global data, and then a whole bunch of tables, one of which is the stir tab, or the, whoop, that's supposed to say sim tab. We got the symbol table and the stir tab, string table, and a whole lot more. But for the object file example, I've got a readelf output here. Readelf is your best friend when you're trying to understand how linking works, when you're trying to understand how elf files work. All of its options are great at explaining exactly what each of these sections contain, and explaining to you how big each of these sections are and all that sort of thing. So this is going to be the output of the compiler. It's an object file that has all of your code, all of your global data, and it's going to have a list of symbols that may or may not be present in that actual object file. So your actual definition of main is going to be in main.o, but the definition of printf is probably not. So that symbol table will still say this object file needs access to the symbol printf, but it's going to be there as an undefined reference. So you get a whole bunch of these elf files as output from your compiler. Okay, so what does the link editor do here? It does two main things. It merges object files and it handles relocations. So merging object files is pretty straightforward. We have all those sections from every single object file. It's going to take all of the texts and mash them together and output one big text section. It's going to take all of the data sections, mush them together, and make one big data section. And the output of that, if you have an executable, is going to be, for statically linked, it's going to be an exec file for the type here in the elf header, or it's going to be din, but we'll get to that in a bit. And the second piece that it does is it handles relocations. So like I mentioned earlier, each object file is going to have a list of external symbols that must kind of be resolved at link edit time. This is going to be, oh, I'm linking libc.a, I need to have access to printf. The link editor is going to be responsible for making that happen. Yes, question.
When you do relocation, how does it manage doing like absolute jumps? Are those in the object files stored as like relative offsets that are only made absolute at link time, or are they absolute and then translated?
Like a switch statement kind of absolute jump?
No, like more like a call.
Okay.
Like a call to an address.
I have an example later, but the question is, how does the compiler, or how does the linker handle absolute jumps when we're doing relocations? The short answer is that the relocation is going to have one of several different types, where the type of relocation, well, how do I put this? Each relocation is going to be an entry in the relocation section of the elf file. So here we have rel.a.text, that is your relocation section. Each of those is going to be an entry in like a giant list of relocations as big as the size of the section. Each of those relocations has a type, where the type tells you, tells the link editor or the dynamic linker how to transform the data in the relocation with the data in the location of the relocation. So there might be information in both locations. And based on the type of relocation, it will either say, do a program counter relative relocation, which is very straightforward, where here, based on the address of this instruction, do something. And for statically linked libraries, the link editor can just slap that in there and say, we're going to load this at address hex 1000. And therefore it knows that this this instruction is at this exact, going to be loaded at this exact location, and fill in some exact offset to where that jump is going. But for a dynamically linked case, that's not, we're going to have to leave that relocation there for later, which I will get to in a bit. So did that answer the question?
Yeah, that's awesome. Thank you.
Okay. So for merging object files, like I mentioned earlier, we're going to bring back this diagram, but what it's going to do is it's going to scan all of the object files that are input, including your static archives that you pass to the linker, including static archives that are implicitly passed to the linker by the compiler driver, like it's going to implicitly link libc unless you tell it not to, that sort of thing, and it's going to scan through all those, merge all those sections into your final executable. So that's the basics of merging output files. And I have in my references a talk from Rui Oyama, who is the author of the mode linker, and also the initial author of the LOD linker, where he goes over in more details how exactly this merging of output files works. So I don't need any emojis, thank you. Please go away. Mash on my keyboard. But his talk also goes over how the mode linker is actually able to do this merging and relocations at only twice the speed of copy, the copy command on the terminal. So it's possible to do this really fast. The GNU linker will not be doing it twice as fast as copy. It'll be doing it, or twice as slow as copy. We're doing it like 30 times as slow as copy. But okay, so how do we inspect these relocations when we're building something? So here, I took this, simple hello world program here written in C that just puts hello world, and we're gonna take a look at the object dump and the assembly for this to see what's actually happening. So there's a couple things to point out here. The first one here is that when I pass the R flag to object dump, it's gonna tell me, okay, so here at byte offset 10 or so, there is an entry in the relocation table of the ELF file that says, okay, here we have a relocation for x86 64 that is a PC relative relocation that's going to be 4 bytes big. And so this LEA here is actually loading the address of hello world, the string. So the way this assembly works is it says set up stack frame, load the address of hello world, call puts, unset up the stack, and return. Right? This is a very simple program. Hopefully this assembly doesn't look completely unmanageable. And the thing to notice with this is that actually, so I think these 3 bytes are the opcode for LEA, and then the next 4 bytes are actually zeros. So if you actually go poking around an object file, or in some cases an actual executable that's dynamically linked, and you try to figure out what addresses are we loading and whatever else, you're going to see all sorts of zeros everywhere that don't make any sense. And that's because there's actually a relocation that corresponds to that address in memory. So when the link editor takes this object file and turns it into an executable, it's either going to fill this in with an absolute address, or it's going to fill it in with, or it's going to translate that link editor relocation type into one for the dynamic loader to handle. And the second one here is that the call to puts. Now, object dump is smart enough to figure out that this is actually saying, here's a relocation that goes to the procedure linkage table that goes to the puts function, but we're going to talk about procedure linkage table later. Okay, I think that's everything on the slide. So, any more questions so far? Yes?
Are B and 13, are those like line wraps and baby blocks? Or is it like indentations?
So for this indentation here, what do the B and the 13 mean was the question. So the B here is actually telling me that at offset B of the file, or maybe it's of the text section, that's what this relocation is pointing to. So at hex 13 is where this PLT32 location is going to. So at offset 12 we have E8, and then we have 4 bytes of zeros. That 13 is hex 13. That's what the relocation is for.
So it's not a line wrap?
No,
I thought
it's additional data.
Is that how object dump?
This is a screenshot of object dump on my file. Was there any more questions?
I was just agreeing.
It's telling you what all the zeros
There's
mean.
additional information that goes with line 8.
Yes,
It's not, that isn't representing data that's hidden in file at that offset.
correct. That is additional information inserted by object dump. If I didn't pass R, it would not have that information, and I would see a bunch of zeros and then be like, what is this data it's loading? I have no idea.
So that's information that got from some other section in this file. Right?
Yes, we grabbed that from the relocation section.
I have a question just about getting orientated here, because I feel anytime I see assembly, I'm like, what system am I on?
Mhm.
Does ELF imply that I'm on a Unix operating system? Like, I've only ever seen it on Unix, but I don't know. Maybe it works other places too.
How do I put this?
It implies non-Mac OS.
Yes, so
See, that's Unix based.
most Unix systems, well, I think almost every Unix system uses ELF these days. I guess is one way to answer that question.
So
But-
if I see ELF, an ELF file, and I've got the assembly language here, I'm on a Unix system. That is probably not Windows.
You are absolutely not on a Windows system.
Okay.
But Mac OS uses Storm, right?
Mac OS uses something called Mac O, which is like ELF but better in every way.
Oh.
But I don't know anything about it other than it's better.
Because I told you it was better.
No, because the way it's better, it's not better in every way. But the way that I see it as better is because the way symbol resolution works on Mac OS is that it's a 2-level lookup table. Like on ELF, all of your symbols are just in the global namespace.
Okay.
At as far as the linker is concerned, all the symbols are global. But when you link against a symbol in on a Mac-O platform like Mac OS, iOS, tvOS, whatever, the information about that symbol includes the final object file that it's part of. So if I have, you can't do symbol interposition on Mac-O.
So if I see file format ELF for all practical applications, it's safe to assume you're on Linux.
Well, I'm going to show you an example later where we're not on Linux. We're going to be on SerenityOS. But yes, you can assume Linux or FreeBSD or NetBSD or OpenBSD or Dragonfly BSD or
It's not, yeah.
or Linux.
Thank you.
Okay. Yeah. So people were asking where that information came from for this this relocation here, the PC32 and the PLT32 relocations, and what do these offsets mean? So if we actually ask readelf instead of object dump, it will tell us what's going on. So we have two relocations for the text section here that were, so these relocations were actually created by the compiler or by the assembler or by both of them having a party together on your command line. But I don't really know which one of them creates it. But yeah, we've got one here that is pointing to offset B, one here is pointing to offset hex 13, and one of them is a PC relative relocation, and the other one is a PLT relocation. And some of this, I believe this information actually indexes into the symbol table, at least for this one. I believe this 5 here says symbol number 5, and that's how it knows that it's puts. Whereas this one just says we're in RO data -4 for this relocation. So yes, so when you have tools that are iterating over your object files like a linker or something like readelf or object dump, they're going to be loading up the ELF symbol table or the ELF section header table, and they're going to be looking at all these section headers, and in order to make sense of anything in the file, you have to go poke at 3 or 4 different tables in order to figure out what's going on. Like this this symbol table at offset 5 doesn't actually say there's a symbol called puts here. It says there's a symbol whose name is this offset in the string table, and you have to go read the string table to figure out what the name of it is. So that's quirks of ELF. That's what those relocations mean. Okay, so what happens if we actually link this thing statically? What are we actually going to see in our main function? So when I did this object dump, it started filling up my whole terminal because it included all the contents of libc, so I had to pipe it through less and then copy just main function. So this executable file is obviously bigger than just the relocatable object file because it includes enough of libc to be able to call puts and see hello world on the terminal. So our LEA here, our LEA here is no longer a bunch of zeros, right? It's actually a specific hard-coded offset from the instruction pointer. And so in the final object file at offset hex 4177D is where this instruction is, and at some later location in the file is where our actual string is. And it is quite far away, as you might have noticed. But there's a lot of libc in there. And also our call to puts has now been fully resolved into a call to glibc's internal function called ioputs instead of just the C. Instead of just saying puts, the linker did a bunch of magic and figured out, oh, okay, we're actually going to call this function here, and it is relatively close, I think, for C. Kind of close.
It's closer than the other one.
It's closer than the other one is. So this is what the link editor is doing when you link statically. It's taking all of your object files and it's taking all those relocation lists, it's resolving those relocations while at the same time outputting all of these sections and laying them out in a way that doesn't suck, essentially. And this is where things like link time optimization can start reorganizing where each object file's data goes. And if you have something like F function sections turned on in your compiler or F data sections, then it gives the linker even more ability to reorder things so that they might be better.
So this object dump of main, is that like the text section,
Yes, that is part of the text section.
and then the like load effective address, call, that offset, is that always going to be in the text section, or could that go to a different table? Is that like a string table, or?
So what the compiler and linker are assuming about the way your operating system works when it's going to load this application is that it's going to load the text and data together as a group into memory.
Okay.
And so it's going to know that there will be a fixed offset between that program instruction and the data section that's going to be after all of the text.
Okay, so that offset would be in the data section.
Yes, that is an offset to the data section where our string hello world lives.
Okay.
Any more questions about our fully statically linked?
Because if it's in the data section, what's the instruction here? That's the offset.
So the reason why we want to do instruction pointer relative offsets is so that we can have position independent code. So when we do position independent code, we're loading the base address of the executable image is going to be somewhere in memory. We don't know where. And we do this for address space layout randomization reasons or other reasons that are part of an OS class instead of the talk on linkers. But we do PC relative to support that for the most part. Okay, so we now fully understand static linking, maybe. So let's go into why we might want to do dynamic linking. So if we look at static linking, why, like what it's getting us, it has a couple advantages. One of them is that at load time, all functions have a known address. And so we can just jump directly to them and whatever else. And if we find that, oh, this group of functions are too far away for our, offset and the instruction pointer, maybe we can move them closer. Like it lets the linker play games. Generally, linkers don't like to play games, but it lets you do that. Also, all code is in the same ELF image. All code is going to be co-located, which in theory lets you do cache-friendly things. This is something where there was a project out of Meta called Bolt, which has recently merged into LLVM. And the whole point of that technology is that they profile your application so that they can reorder all of the functions and whatever else to be more cache-friendly and increase performance. So that's a plug for Bolt, I guess.
Have you actually used Bolt?
No.
Okay.
Yes.
You have? I've
Question?
only played it.
Is that late time optimization of VR?
Yeah, Bolt is a form of link time optimization, but also
It's kind of like post-link time
It's
optimization.
profile guided link time
Yeah, it's-
optimization.
I was told recently that if we actually changed all of our functions in inlines, all of a sudden our performance would go through the roof. It's no, LTO will do it for us. And I'm like,
Yes, LTO will do it for you.
yeah.
but can it do the wonderfulness of like eating up inlines and just disappearing?
Yes,
Yes.
LTO can eat up your inlines and disappear them. Though I think, yeah, there's different kinds of LTO. There's profile guided LTO and non-profile guided LTO. Each of them has different trade-offs, I guess. There's probably at least 5 LLVM developer meeting talks that go over all the kinds of LTO that they're doing.
How far along does anyone know how far along Visual Studio is in LTO stuff right now?
They've had LTO for a long time.
Yeah.
I guess I'm the one who can answer. Does anyone else do Visual Studio work?
This is an
Okay.
ELF talk.
We want to.
We asked you about Visual Studio for this is an ELF talk.
Yes, Visual Studio supported LTO for a long time.
And all for our still is much slower than
Yeah. I think the build time is
runtime is faster, obviously.
And that's what you're paying for.
Yes. Yeah.
Okay. So why would you not want to do static linking if it's so great? Well, another thing, well, I said before that all code is in the same ELF image, and that's great. But also, all code is in the same ELF image for every single program in the system. Which means that if you have hundreds of programs on your Linux system and they're all statically linked, you have hundreds of copies of libc, lib standard C++, of libcurl, of whatever else, and it increases code bloat as the number of programs increases. So, right. Also, updating a library dependency requires relinking the program. And for you distributing your application, you don't care. for people who are managing things like Debian, they care a lot because it's a lot easier to ship an update to libc than it is to rebuild the entire OS and ship you an update to every single package at once. People would be kind of upset if you had to update every single package at once instead of just updating libc. So another thing, think CVEs. You know, in another 2 weeks, we'll probably have another OpenSSL CVE. They tend to do that on the schedule. But when you want to update OpenSSL, you want to just, you know, ship a new package and you'll be great. So with dynamic linking, you don't have to do that. Yeah. There's a question way over there.
Does the linker chuck in functions that you don't even use? Like, if you're pulling in a library and you're just using one function from it, is it free to statically link, or is it a terrible idea? Because then you have all of those functions from that library.
So if you are statically linking a static archive, the way the linker decides what to do is it pulls in, so an archive file, the .a files, they are simply a list of .o files with some metadata at the front. You could probably use a tar.jz file or something, but everyone just uses this bespoke archive format. So when the linker decides, oh, okay, I need a definition of this symbol, and it goes into the archive and it says, oh, this archive has this symbol, it will pull out just the object file that provides that symbol into the executable. So that's why things like muscle libc, if you look at their implementation on their Git, every single function is its own .c file, because that's how static linkers work.
Well,
Thank you.
isn't it sections that we need to think about? Linkers deal with sections, right? It's not.
They
It's
can.
not really functions or object files, but it's the sections within them or whatever.
Yes.
Is that right?
So if you do something like -f function sections,
Yeah.
it will give every function its own section. And if you enable something like GC sections on your linker, then it can eliminate sections that are not referenced anywhere. But even without doing GC sections or f function sections, it will do that object file extraction.
Right. But I guess if the person who had made the archive had turned on f function sections in making the archive, is that possible, or is that the thing that happens later?
I think if you
Like-
turn on f function sections when you create an archive, then the executable that links it will only get the benefits of that if they turn on GC sections to garbage collect unused sections.
Okay.
Okay. Any more questions as I read the last bullet here?
I just want to clarify. By archive, you mean .a,
Yes.
like a static library.
Static library, yes.
Okay.
Created with the AR tool or LLVM AR, depending on which tool chain you're using. Okay. Another disadvantage of static libraries is that when you change one file in your edit, test, compile loop as a developer, you have to relink the whole program, which might not be a big deal if your program is, you know, a bunch of header-only templates and you have a bunch of test executables and that's it. But if you have, 10 libraries and 100 files, that's a lot to link. And if you're linking like Chromium with 30,000 files, a million lines of code, you don't want to have to sit there for 2 minutes every time you add a print statement or, change one function.
2 minutes.
2 minutes if you're on Google's build farm.
Yeah.
That's a file with less, but that's not 2 minutes.
That would be
Well, with mold it is, but what's
I have a somewhat serious
Yes.
question for the more experienced Windows developers. How much does incremental linking on Visual Studio help or not with this kind of problem? It's turned on by default, right? Debug. And debug only is incremental.
Incremental linking is mutually exclusive with LTO.
That would make
You can't,
sense.
you can't do that. It's a debug helper.
Right,
Does
right.
Is it the same technology as edit and continue? Is that
Yeah,
basically the same?
I
thing?
think it's, yes, I think it's,
Edit Country also enables function level linking, basically the previous topic we were talking about.
okay.
Yeah.
They also, I forget if they did this with, if it was Visual Studio or not, but they had like some blank space at the beginning of most functions. So if you want to replace a particular function in your runtime, you can like insert a jump statement there.
Oh.
And
it's a very old school optimization.
But they do it behind the scenes for you.
I believe so, yeah.
Okay, so what am I trying to say here? Where was I? Okay, so there's disadvantages of static linking and dynamic linking fixes all of them, right? Okay, so what is exactly is happening when we're loading the program into memory? Because that'll help understand how dynamic linking actually works. So I grabbed this image from somewhere and linked it in the notes, but so here on the left we have our ELF file on disk. It's got all of its, it's got its text, it's got its read-only data, it's got its data, it's got also other stuff. When we load this into memory, someone has to do that. Someone has to take the data from the file system and put it into RAM, or put it into somewhere else if you're on some weird embedded system. But all this memory has to be, set up with the right page tables so that it's the correct executable permissions, write permissions, read permissions. It has to be the right spacing apart, and we have to set up a stack. We have to initialize the heap to be after the stack, before the stack, whatever, who cares? So someone has to take the data from the file, put it in memory, and jump to it. For statically linked, kernel does that. For dynamically linked, we need to have a program that knows how to do that. Because your program, you probably shouldn't be putting logic into every program that knows how to relocate itself. Unless you are the glibc maintainers, and then you have to do that. But right, so for dynamically loaded binaries, the kernel is going to load the loader and maybe your application beside it, depending on the operating system you're on. And then the loader is going to make sure that the execution environment is set up according to, the System 5 API or something like that. Okay.
Is that actually put into the header at the beginning of the ELF thing, the thing that actually goes under libld-linux.so?
Yes. So inside your dynamically linked executable, there is a specific section called pt_interp for the interpreter, program interpreter, and that'll be I don't know if it's actually a string or if it's just a pointer to the string table, but it will tell you the name of the application or the name of the file that is the loader. And that's something that you can manually set yourself with the -- dynamic linker flag to most linkers, but
it's a lot of fun and embedded when you accidentally remove that.
Yeah. Generally, you don't want to set that unless you're somebody like, I think there was a talk at CPPCon in 2019 where Amazon AWS folks were saying when they were setting up AWS and Amazon Linux, they had a wrapper script that would use their own specific version of the loader. I don't know. You can look that up if you want. Okay. Just throwing knowledge out here. So for dynamic linking itself, one of the things we've said that was bad about static linking was that we've got copies of the code everywhere. So suppose we want to share code between executables. How do we do that? The canonical example that was pioneered by some mix between Sun and Windows, I don't know who did shared libraries first, but I think in the Unix world it was Sun, is shared libraries. So this is going to be some other ELF file that is just a bunch of code, which may or may not have static initialization as well. If you have globals in your shared library that need static initialization, you're a bad person, but people do it anyway. But the key thing to understand about how shared libraries work is that your executable is not going to have all external references resolved at link edit time. So you're going to get to the end of linking, you're going to have your main, and it's going to say, okay, printf is not here, it's still undefined. And there's going to be an entry in the ELF file that says, okay, when this is loaded, we need libc.so. So, yes, so any of these unresolved references are going to be from some library that we are linking, or from some library that some library we're linking is linking. And so, yeah, so we're going to link with unresolved external references at compile time. You can play clever games like, say, -- no allow schlib undefined or whatever the flag is to make sure that you pass all of the shared libraries on the link line that define it. Otherwise, you can, I'm sure everyone has had the experience, maybe, if you use Linux systems where you run an executable and it says, unresolved reference to mangled symbol. And you're like, oh, right, I forgot to write, my destructor in the CPP file. Or I forgot to implement this function, but it was undefined. So that flag doesn't help with that problem, but it helps with, you link them on shared library. Anyway. So we're, in essence, deferring the work of resolving these shared library symbol references to runtime. And it's the dynamic or runtime linker's responsibility to actually set up this program, set up your program with all of its shared libraries. Okay. So how do we represent these unresolved references? With, of course, another level of indirection. So instead of managing all of this through the ELF symbol tables, we're going to manage this through some runtime data structures, namely the global offset table and the procedure linkage table. So inside your ELF file, yes. So inside your ELF file that's actually fully dynamically linked, there's going to be like 30 sections instead of 13 from the object file. And one of those is going to be the procedure linkage table. One of those is going to be the global offset table here. There's also the PLT dot, but we can ignore that. So these two data sections here live in memory that is going to be loaded at runtime. They will exist in memory at execution time. And your program will be referencing the global offset table and the procedure linkage table during its execution. So the global offset table is going to be a table of pointers to global data that is either I think for the most part, it's going to be things that are external, but you could put things that are internal and have the linker relax those relocations. Anyway, so initially this thing's going to be filled with, it's either going to be empty or it's going to be filled with directives to the loader that say, when we load this thing, you fill this in with this symbol and that in with that symbol and whatever else. Procedural linkage table is the same thing, but for function pointers. So when you, inside the actual executable image, the procedural linkage table is going to be filled with a bunch of incomprehensible, weird data that doesn't disassemble properly. But what it is going to be is telling you which relocation entry in the dynamic relocation table corresponds to this PLT entry, and then a stub of function code that the loader is supposed to fill in the arguments for to call into the loader to do the relocations if you want to do lazy loading. Which we can ignore because it's complicated. Okay, so how does this actually look? So when you're loading a whole bunch of shared libraries alongside your executable into memory, let's resume this gray box in my crude model is memory. Every single image, where an image is either the main executable or a shared library, is going to have its own global offset table and procedure linkage table specific to that image. And the loader is going to have to fill in all of those references for each image. So if you have, two shared libraries that each reference a symbol from a third shared library, each of those shared libraries gets their own PLT entry to call into that other library, and which means each time you call into that other library, you're going to get yourself a nice indirect jump to hop first from where you are in execution to the procedural linkage table. The linker patches that table after it resolves the symbol, and then you're going to jump to the other shared library. So I guess one thing to keep in mind if you want to have 30,000 shared libraries is that every time you jump across a shared library barrier, you're getting yourself a nice indirect jump through the PLT. Okay, and something else to keep in mind is that the offset between the procedure linkage table and the global offset table is always going to be fixed. So when we do PLT relative jumps or something like that, the way that most application binary interfaces do this is that you have one register reserved to point to the global offset table, unless you're on 32-bit x86 and where you only have 4 registers, and you have to insert a thunk to get the address of the global offset table based on the current program counter. But you do those jumps based on the pointer to the global offset table. Okay, and in this picture, imagine there's arrows from each PLT to the text section of every other image, and pointers from the GOT of each image to the data section of every other one. Like there's pointers everywhere. Okay, so how does the loader know how to do this? Is through the ELF dynamic section. So that's this one here, number 23, dynamic. So this one contains, and I'll show it on the next slide, a bunch of data for the loader to read when it's actually loading your program, to understand how to find the symbols that need resolved, how to find the libraries that you need, and stuff like that. I think that's mostly it. And there's also things like dinsim, dinster, relay.din, and relay.plt. So these are, for the most part, optimizations. So the dinsim and dinster are smaller versions of the symbol table and string table for the executable that only includes entries for symbols and strings that are needed during runtime relocation. Because if you had to have the entire table, these things are giant hash tables and whatever else, and the system 5 hash sucks, so everyone uses the GNU hash. But the size of the table directly correlates to how long it takes to find your string in it. So the linker will generate these dinsim, dinster, these relocations for the loader to use, and make them as condensed as possible so that the loader doesn't have to spend very much time relocating the entire binary. Okay, and I guess another thing to note is that actually doing this relocation on large binaries takes a really long time, which is why things like lazy binding of PLT entries is a thing that exists that you should not use because it's a security risk. Okay. But it was a great idea in like 2005. So main jobs of the loader, and I just smacked the microphone. Great. So it needs to relocate itself, which is related to that position-dependent code thing I talked about earlier. It needs to load the main program image into memory if it was not already put in place by the kernel somewhere, and the kernel told the loader where that is. It needs to scan the dynamics section, which, like I show here, has needed entries for shared libraries you have. It has the location of your static initializers. It has the location of your global finalizers. It has a location of a hash table for symbols. It has the location to all this other stuff. What else? Some flags, like this one says bind now, which means don't do that lazy relocation trick. Also version symbols if you're on Linux. Okay. Yes. So it loads all those shared libraries and shared libraries that those shared libraries need and shared libraries that the needed shared libraries need, all the way until everything is resolved. It also relocates all images to the load address, which maybe happens earlier, and resolves these unresolved symbols. So there's going to be the required unresolved symbols and the maybe not required unresolved symbols for that lazy loading optimization. Okay, so we may or may not have time for a demo. I think we do, assuming people are on board.
Timer, dude. You can just go into.
Oh, yeah, I don't know.
All right. So we're going to look at some code here in the C line.
We're going to look that up for 45 minutes, just for the record.
Okay.
It's only barely simple for a while.
Yeah.
Plenty of time.
I talked too fast, so make sure you check the recording. Okay. Any questions coming up to this part before we hop to the demo?
I have a question about a clarification I'd like. You said every time I call a function that was loaded from a dynamic library, it has to do that double indirection.
Yes.
Every time.
Every time.
It doesn't ever, like, I don't know, rewrite your text section, so it doesn't have to do that or something.
You absolutely do not want to be able to rewrite your text section.
Okay, just make sure.
The ideal situation is that once your text section has been loaded into memory from your shared library or whatever else, the loader immediately protects that as exec read, and it's never made writable again.
Okay.
Because if it's made writable, then you can have a security problem. This is why things like OpenBSD and SerenityOS have write XOR execute things built into the kernel and the loader to make sure that once a memory region has been marked as execute, it can never be made writable again.
Okay.
This is something that you can do in Linux. It's the reason JIT works, is that you can write and execute things. On systems where write XOR execute is a thing, people have to play games with like multiple mappings to the same virtual memory.
So it's still possible.
It's still possible. It's just, I don't know. I'm lukewarm on JIT.
Isn't that where things got messed up recently? The XC?
I don't think the XZ problem was related to mapping.
Yeah. Because there's a moment where you can actually write
Yes.
jive with whoever that is, took advantage of that to introduce backdoor.
I think the technical details of that are something like during the resolution of symbols for OpenSSL or something, it inserted something to execute some other code through an ifunc, which is a way to, at runtime, select which version of a function you want to call. Generally use that for something like, I have SSE mmap, I have AVX512 mmap, and I have crap mmap. And based on which CPU I'm running on at load time, I'm going to choose which one of those I tell the loader, this is the location of mmap.
It was a very narrow window with.
Yes.
After that, you couldn't achieve.
Right, because if your distro has set up the defaults for the system compiler correctly, it will resolve all of those symbols. It'll do bind now or -z bind now to the loader, to the linker, sorry. And then the procedure linkage table will be marked as not writable after relocation is completed. And then you won't be able to overwrite things. So that's messing with the global offset table and procedural linkage table is something you'll see in cybersecurity literature where people are talking about things like return to libc or other techniques that involve overwriting the pointer to some common function that's going to be called by the program to your untrusted input that got a buffer overflow or something like that. Yes?
I have a very specific picture in my head, and I don't know if it's outside the scope of this talk, but I've done written code that does dynamic, like loading your own modules, C++, right? So DL open, DL sim to get a symbol, and then you have a pointer to the symbol, and you now you can call that symbol.
Yes.
You're just kind of doing this thing manually in a way, right? What happens if I DL close?
Don't.
I'm just asking. But what technically is going to happen here if that library gets unloaded, and then you still try to call a symbol that's in there?
Hopefully a seg fault.
Yeah.
Something else might happen.
I'm just trying to think through the double jump process that you explained. What's that?
Still be there.
It might still be there, but
the
if
descriptor
it,
can be closed, but the memory pages will still be there unless you unmap them.
I mean, I think like the GNU loader probably, I don't think it M unmaps, I think it just M advises as don't need or something like that. Which basically means
That's not.
it means it's gonna keep that virtual memory reserved, which we can do because we're 64-bit and we don't care about virtual memory sizes
And
anymore.
that way you can't accidentally put something else in SM address and get non-thing.
But it should also mark it as not executable.
Yeah.
So then you'll get the seg fault.
because you're trying to call like some execute something that's not executable.
Yeah.
Okay.
Yes. But also I think like muscle libc just doesn't implement DL close. And POSIX says DL close might work or it might not.
we had a plug-in system that if you tried to unload it, it would just log saying, I'm not going to do that.
You're nuts. Go away.
Well, it's an interesting problem though. If you have a plugin system, your users sometimes want to be able to reload that module or reload that plugin.
Our problem is that once you might actually have our plugin system sometimes works like under a library barrier that multiple people might use our plugin system. So we could have 3 different dependencies that all load from the same set of plugins, which could, so if any one of them starts unloading, it can start breaking other parts of the system.
Okay.
And I mean, the general advice is don't DL close.
Okay.
If you really want DL close to actually DL close, you have to be very careful about how you do it and make sure that you don't have those dangling pointers into that memory saved somewhere interesting.
And you're saying on some
Reloading is probably a lot safer than closing.
What is sorry?
Reloading is probably safer than closing. You probably open it a second time, the new version. Use that
Yeah, is there a DL reload of some type or place or something like that?
I think just
No.
But if you do DL open again, it should say that's already opened and already linked. So I'm not going to do it again. There probably is a flag. You're right, because there's like this many flags to DL open and DL sim.
And most of them only work if you're using GNU. So
We just kept them like
Yeah.
global table to the whatever function is the entry point to all plugins, and then you could only add to that global table.
Okay.
So if somebody later came along and asked for the same plugin, you would just not load it again and go find it in the global table.
Right.
Yes.
So are you going to come back to this question about the jumps or the references? What was the question?
It was about absolute addresses.
Yeah.
So we kind of covered it with the relocations, exactly how that works.
Because, like, for Simple Plus specifically, there was a time also when if you wanted to throw exceptions across library boundaries, it got kind of messed up. And already for a long time, it behaves the way you would expect it to behave, but it's sort of similar to that.
Yeah, I think the specific issue you just mentioned of throwing exceptions across libraries being a problem is like a Windows thing, as far as my experience goes.
Oh,
Because
it's on Linux.
yeah, as long as I've used Linux, which is not that long because I'm only 29.
Do you have a reference for what year you're referring to? If you don't mind my asking. Because I've also never seen this problem, but I've heard about this
I've
problem.
thrown exceptions since early 90s.
It also might be the library and the application being our compilers.
Well, there could be an ABI issue.
ABI issue.
I remember reading about the problem, but never having it since early 2000s.
Yeah, that sounds about right.
Okay.
Well, that might correspond to when they switched from set jump, long jump to the current table-based exceptions. Maybe. Yes, question?
Can I just ask a higher level question?
Sure.
Can you just give like some practical advice to everyone as to why you use static linking versus dynamic linking? My general rule of thumb is if I want to distribute a program to somebody, I use static. If I control the system or if it's in the cloud, it's dynamic. But
I
can you
think
just give some advice like in terms of memory size or how you're distributing the program or what else is running, what you would choose and why?
Well, I think it's kind of similar to the issue of system package managers versus language package managers, where if you're a developer and what you want is exact tight control of exactly what version of a library is being used when your application is distributed, you might want to statically link to like bake it into the binary. Whereas if you want your application to play nice with the rest of the system and be upgradable with the rest of the system because it's some, like say you're making a Linux desktop app like, I don't know, like KDE Kate or something, you might want to have some of your libraries that are either internal to your application or the ones that you link to in the system be shared so that they can be updated separately from the main executable.
You just described like commercial versus open source difference. If you're distributing it commercially, you pretty much statically link it.
Right.
It's not.
Don't statically link OpenSSL.
Another example in Windows land that is kind of similar to the package situation in open source is if you've ever installed a Windows program and had to go and install
the MSVC runtime.
Yes,
I have 25 versions installed right now.
Yeah, that's a case of like
That's probably
all
a lot
that
less
stuff
than you would if they're all statically linked.
And our software, we actually bundle up the URLs into our installer so the user doesn't have to separately install that. That's something that's dynamically linked. You can't have that.
There's a lot of security issues that are all one-offs. Like you have to decide for yourself for your program because, like, if you link OpenSSL now and then there's an OpenSSL vulnerability, your code is potentially vulnerable.
And you have to redistribute it.
Yeah.
You also have that CDP.
But also, if you're writing something that you don't want someone to DL open their own version of a library, then you need to statically link it. Like, for example, if you're writing a software licensing system,
Exactly.
yeah, you don't want someone to dynamically link their own thing that says that it's always licensed. So it depends on what your application is and what the needs of it are. But there's also
Yeah, I mean, another one might be if you're trying to link something that's LGPL licensed, you absolutely want to link it dynamically because otherwise your code becomes GPL.
Yeah.
I don't think that's tested in court yet. I think
maybe.
I think if Free Software Foundation will claim your code is GPL anyway, even if you don't make I think the courts have yet to test that.
You could choose to statically link LGPL code and distribute LGPL code.
What about the standard library, C++ or C?
I think
What do you do there?
if you think it's possible that, what am I trying to say? If you really want to control exactly what standard library symbols are in your application, you could link it to yourself statically, but I think for the most part, you probably don't want to do that.
Chromium statical links, at least on Windows, everything is static.
I believe that. And that's why you have to update it like every 5 years.
Yes.
That's why.
But that's why they don't, I mean, they don't get new bugs under their, Microsoft cannot introduce bugs to Chromium because of way updated Visual Studio.
Yeah, I mean, Chromium also like builds lib standards, libc++ from like some arbitrary commit all the time. They just bump their revision, which is some distance from trunk.
When I worked on contracting on an alphabet project, we had Chromium in our code base. We actually had LLVM from some commit that we bootstrapped.
Yeah. Yeah, that's how Chromium does it. They do all sorts of weird stuff.
Because apparently when you're building a robotics project, you have really strong opinions about the commits of LLVM.
In no other place does anyone have strong opinions about that. It's really everyone's chill. I'm a gamer in the world, definitely.
Yes,
I'm not
question?
fighting any battles about C++03. No.
I'm not sure, maybe you're still going to address that, but that's been a long time since I've read that. But there's also other, say, formats, image formats, and I remember like cough and things like that. But I recall reading that because it's C++, some of those other formats were incapable of actually handling C++ code, ABI. Is that something that you're going to talk about, or is that something that you've come across?
Certainly not going to talk about it because
Okay.
this is the elf talk, but
Static linking is kind of universal.
yeah, but
I'm not related.
I mean, as far as other formats, like I know of COF and PE and XCOF and Mako and the A.out format from the 80s or whatever it was, but I'm not really familiar with the constraints that C++ had on those formats.
I know the book, which is linkers and loaders.
Yep, it's in my references. I have my own copy.
Levine, I think, was
R.L. Levine, I think.
Yeah,
John R. Levine.
Like Lexiniak, but
yes,
he. I think in that book he mentions that there are the other formats actually have restrictions on language like C++, and I found that fascinating at the time, but I can't recall exactly what the issue was. If I would have to guess, I would think it had to do something with RAII or something like that.
yeah. I mean, I read that book on a plane a couple of years ago. So
Maybe
I
that has
don't
to do
remember.
with the load time globals. I mean, in other words, code that ends up running as soon as it's loaded.
Yeah, I know.
I don't know
The
what
only
that hook
thing-
is, but there needs to be in C++ standard a hook that actually runs when the code's loaded universally without calling name.
Yeah.
Yeah, but all you need are different sections, conventionally called ini and fini, right? And then
Yeah, but
you can write your own linker script and startup code that calls that function pointer table.
Yeah, but the other formats, do they actually allow that?
It's just code. Well, how would the format disallow it?
And that was the interesting part that I was reading. I'm not sure it was specifically about that issue, but I have the book, and I think it's also like really downloadable.
Yep. Yeah. If you go to this website, I think you can get the PDFs of each chapter,
Yeah.
or you can buy it on Amazon for like $50 or something. But that is a very good book. Okay.
There was a comment from online. I gave it, Ashley says this, I gave a talk at CPP North about static initialization and how some of the bootstrapping code works. Not sure when the video will be released though.
Okay. Thank you for that. Okay. Let's take a look at some code. See how this works on Serenity.
There's one more question.
Okay, yes.
If you have a non-script executable, would you delink a static fluid binary to a then your dynamic link or like a license manager or something?
I think in ELF, linking is a one-way process. I think,
Right, well, I mean,
if you had access to all the relocations, you might be able to do something fun.
You don't know what they were anymore.
Yeah.
That's why if you had them, you might still have a lot of the information already in there.
But instead of heuristics, you might go.
You might be able to
I mean, if all you had was a dynamic linked executable, you wouldn't be able to delink it without significant effort. But if you had more information about the way it was built, if you had the original object files, you would definitely be able to.
You could always rewrite. Rewrite the file.
Yeah, and
there's a tool called PatchL that allows you to like change a lot of different stuff. I don't know if it can do that.
PatchL, huh?
No, I mean, that was created by the NixOS project because they have very weird constraints for their dynamic loader and stuff like that. So, and fixing your R path and changing the interpreter and all that kind of stuff. That's what
Well, you
they
didn't
use
get
it
into
for.
RPath at all in this talk.
You can give that talk if you want.
No,
that's
that's all right.
that's another hour-long talk. Okay.
Cool.
So let's look at C-Line here. So here I
I
have.
was just going to say, you got to talk about version conflicts with two different things grab onto two different versions of the same DLL. The official spawning of DLL held.
The disadvantages.
Oh, are there any disadvantages?
I mean, that generally on Linux, that if you have a different SO name in the if you have a different SO name, then everything's fine. If you don't, then good luck. Okay, so this is SerenityOS source code. We're here in the kernel. We're at the exec.ve system call.
Can you embiggen it a little bit?
I already did that twice.
That's part of being a presenter.
Yeah, I mean,
Control Shift Plus on a lot of apps.
Control X, Control.
Oh, it's a Mac. There's no control.
That's why I don't know what the button is.
Yeah.
Control Shift Plus.
Open Apple.
Yeah. Okay, this should be legible, more or less.
It's better, yes.
So this is the entry point for exec.ve. It comes here from the system call trap handler.
Why does your function name have a $sign in the middle of it?
For fun.
Because it can.
I think technically VMS did that way back in the day.
Is the evil place.
But we're doing it because it's fun and it's easy to grab for.
No, I mean that's actually this. I didn't. Is that valid? Yeah.
No,
Yes.
it's kind of correct.
No,
That's
not
it's
valid
valid in
identifier.
26, isn't it?
Really?
Yeah, I think so.
Oh goodness.
We added backtick
So-
and $sign and such to the code.
Yeah. Okay. Yeah.
Remember now.
We'll get to this example eventually.
Okay, so the exec sys call, what it's doing. Okay, let's go rapid style here. So first, copies all of the, copies these parameters from user. But
Is that a sanitizer?
what's that?
Copy text from user, is that a sanitizer?
No, it's actually it disables and re-enables super mode access prevention, supervisor mode access prevention. SMAP.
Okay, got it.
Calls clack and whatever the things are, whatever those assembly instructions are called in x86. But it's a way of copying data from user space without leaving ourselves so that user space can access kernel memory. Anyway, so we copy the arguments. We copy. Yes, this is arguments, whatever. Then later we copy the environment. Great. Then we call exec. Great. So what exec does, first thing is it looks at the front of the file, figure out what it is. So there's two options here. First one is it's a shebang interpreted file. So if you have any file on a Unix system that starts with a shebang, we're going to assume that that's the next text is going to be interpreter.
Does everyone know what shebang means?
Yep.
Yeah.
That's hash exclamation point.
Yeah, it means
Hey, There's also people who just said, I literally just graduated from aerospace engineering school. So.
Okay.
I'm trying to get you as a presenter to make sure you explain these things.
Whatever. It's a Unix talk. Okay. Yeah. That's mostly for like scripts and whatever else, shell scripts, Python scripts, Ruby scripts, whatever else. The next option is, this. I should patch this. We only load 64-bit binaries these days, but it's either going to be an executable, like a statically linked executable, or a dynamically linked executable. And the difference between that, like we mentioned, whenever that was, is that the dynamically linked executable is going to have that PT interp section that tells you what the program interpreter is. Yeah, see, we even have shebang here in the source code. Yeah, so first we check for shenanigans in the elf header, but after that, we're into exec. We're going to check a bunch of safety things, security things. We're going to figure out if there's an interpreter. If there is an interpreter, well, actually, this is what actually loads the thing into memory, but we're going to skip that part because I wanted to get to the actual loader.
No.
Bool has interpreter equals interpreter description equals null pointer. No. No.
Define word.
This is explicitly releasing the custody for the interpreter.
Yeah, you can still exchange.
So instead of having a scope here, where after that scope we don't need the interpreter anymore, here we are explicitly releasing that own pointer.
What is the type of interpreter description?
Unique.
Is it a smart pointer?
Yes, it is a unique pointer to...
All right, fine. Carry on.
It's actually a shared pointer to an open file description.
All right, go ahead. Sorry.
We're saving whether we had one, and then we're releasing the resource. Okay.
I only noticed because C-Line squiggled it.
C-Line squiggled it because it wants me to mark it as const. Like, I don't care.
Yes, you do care. Now keep going.
Right. And then we check if it's set UID, whatever else. We set the credentials of this process. At some point here, we get the point of no return where we're going to execute or we're going to crash this process, which should be somewhere around here. Right. Then we generate the elf auxiliary vector, which you can look up if you want to know what that's about, but it's essentially a way to pass extra information to the program that's not in the arguments or the environment. It's things like, well, okay, hold on one second. It's things like what is the file descriptor of the main executable. It's things like what's the page size, what's the base address of the executable, things like here's 16 bytes of secure random stuff. These are things that are generally used by the program loader, but you can also call get auxval on most Unix systems to have a look at that. Okay, go back. Where were we? Come on. Do exactly. Okay. At some point here, we have the main we have the interpreter loaded in memory, and we're gonna, jump back and jump to the main of the loader. So let's go there. Which should be here. Okay, great. How does this loader work? So, yes. First thing it does is grabs the interpreter pointer. You like this?
Just reading it. I'm good.
Okay. Then it grabs our base address and our random value from the random. We slap a memory barrier here because after that we're going to relocate this executable. Because so every instruction above this optimizer fence must be completely position independent. Because we don't know, because our executable for the loader is even going to have relocations in. So we need to relocate ourselves before we can continue execution. So all of this code has to base everything based on stack variables. Then we can relocate ourselves, and then we can access things like C++ class vtables and stuff like that is going to be relocated. Then we initialize libc, do a bunch of stuff there, grab the main executables file descriptor, and if it's not there, we can skip that. And then we jump into linker main. Okay, great. So the dynamic linker in Serenity does a bunch of things. You look like you're questioning things again, Jason.
I'm not going to say a word.
Oh, come on. What is it?
There's a reinterpret cast there, which is not necessary when you're casting the void pointer. You just make that a static cast so it doesn't make people's brains explode.
All right, I'm gonna mark you as co-author on this.
But now why is it failing? Oh, because it's a function pointer.
Oh,
because it's a function pointer, so you do have to use reinterpret cast. My mistake.
Okay. Right. Then we save a bunch of magic functions. So things that where your application needs to call into the dynamic loader for things like DL open and DL sim, we just have these magic double underscore functions because we're the implementation to do that, so that they end up as weak. They're defined in libc as weak symbols, and they're actually defined here when you load the program, which means that static PIE executables don't work because we haven't redone this in libc. But anyway, the fun part, right here. So first thing we do, we map the main executable, which does a lot of things. Then we grab each of its needed dependencies and we refuse to load it if any of its shared libraries have them. Okay, whatever. At some point here, we actually load all of its link main library. At some point, we load all of its dependencies. Maybe we do that in that function. But what am I trying to show? I think that was mostly it. I don't know. I didn't practice this part, if you can tell.
For each in your library?
Yeah, this actually checks how many.
I'm seeing list of the overall emphasis.
Yeah, then we do a safety check.
Lambda all the things.
What's that?
I said lambda all the things.
Right,
oh, yeah.
Line 716.
Oh, map dependencies. There we go. Yes. So this will map dependencies for the executable, which will then recursively map dependencies for their dependencies and whatever else. And at that point, we have, yes, a list of dependency ordered things, and we can allocate our TLS, link the main library, link everything else, drop the RPath promise. Shout out to OpenBSD. Yes. So that's the loader, essentially. We can look at what this mapping does if we want, but I think I'm mostly done here. Yeah, so we create a dynamic loader, which is mostly just a, what's a ref-coded class, but this essentially just holds all of the data for actually doing something with an object as it is resident in memory. This includes things like what's its load address, where are its program headers, what are the symbols in it, how do we access the symbols in it, and whatever else. So yeah, here's a list of its text segments, here's its base address, where's its offset, what are its ifuncs, all that good stuff. Wow, this demo is not going as I expected, but I don't know. Any questions while I have the code open here?
Yeah, some systems like how linkers and loaders are basically the same program, but how is that application?
Right, so that goes back to the definition that I gave at the beginning, which I pulled from Oracle's Sun documentation, where there's the link editor handles compile time stuff, and the runtime linker handles loading and linking of dynamically linked things. So the runtime linker and the runtime loader are the same thing. I think in BSD it's called RTLD for runtime loader.
Okay.
Yes.
So here I am as a past and maybe future again C++ engineer who does not work on an operating system.
Why not?
I pain.
Serenity.
Yeah.
It's open source anyway.
Yeah, if you just tell him to make changes here, he'll list you as a co-author.
Unless it doesn't compile. And then he'll bug this you.
I'm a little afraid after the chastising Jason's but like, let's say I'm writing an application that runs on an operating system. Like, when I'm not trying to hack anything, so I definitely don't need to know ELF for that. Like, what applications are there where understanding ELF really pays off as a C++ engineer?
OS packaging.
Yeah.
Yeah.
Debugging heinous compiler. Like
That's the only time I've ever had to read ELF, but like I didn't get anywhere with that, so I
I've had to modify.
I don't know, I guess
for that nonsense.
Well, another way to rephrase that question is, when do I pull out readelf to solve a problem that I have?
Yeah.
And that would be when I'm screwing around with what libraries are linked to my application. If I'm debugging my build scripts, I might pull out readelf if I'm confused that some dependency isn't linking properly, it's missing a symbol, so I'll pull it out and I'll say, what are the symbols in this application? I might pull it out if
you find ODR violations, or confirm you have one.
Or if you're like, why?
What do you have?
Why
Version symbols?
am I getting this unresolved?
Right.
So
if you're upgrading a library, you need version symbols too, where you end up having layers, and glibc has a big cluster of worked across 20 distros, and my gosh, we had to support everything back to like old ancient glibc up to the latest. Any updates of any type of packaging.
You can use it to understand the linker the way you use compiler explorer to understand the compiler.
right, so if I have linkage issues, readelf is a valid tool for figuring things out there.
Right. Yeah.
So you need to make a new website called Elf Explorer.
Help!
That's illegal.
So,
Don't
you might need to host this in another country.
That already exists, and it's a DeviantArt page.
That's a good turn.
You could have just said Linker Explorer, dude. You mentioned Elf Explorer.
Yeah, so you can use NM if you have issues with symbols.
Readelf over NM or
Optional.
yeah.
I mean, personally, I like the output of readelf better than NM, especially if you pass the -W flag to say my terminal is wider than 80 columns. Thank you very much. I don't know. I find it gives me more actionable information than NM, where NM will just have a character, an offset, and a symbol, whereas readelf will tell me all sorts of
I
different
think NM will actually read the dynamic linking strings. I think readelf is the only one actually. Readelf-D is the only one that lists it all out.
Yeah, I had that output here somewhere.
Had something.
But if you strip the thing, there's nothing, and then I just see as much.
Yeah, this one has readelf-D, which prints the stuff. I don't know. I mean, you might also pull it out if you're trying to reduce the number of symbols in your binary. You might want to check, like, what are the longest symbols here? I mean, you could use strings for that if you wanted, but...
Is it reasonable to think that, like, you could actually do a better job than like, linker optimization has done?
Yes.
Yeah.
If you're...
Well, just like, it's just like using compiler explorer. It's reasonable to think that you can massage your code to enable the tools to do a better job. That's the first thing you think of.
Okay, that's an interesting approach.
You don't want to see assembly to run the assembly. You want to make it so the compiler doesn't.
Exactly. I mean, if you look at the GitHub for Mold model linker, this is created by the initial creator of LLD, and he found that his Mold linker is, well, it's significantly faster than GNU LD, which who cares?
I think that graph is several years out of date. I think
This
it
one
needs to update it.
Mold, it says Mold 2.4. What are we on? 223.
Yeah.
Does he have an updated graph?
He does not.
Dang it. Okay.
Would an updated graph not serve as?
I think the upgraded graph does not look as good because the other linkers are also improving right now.
Yes. So, I mean, maybe not GNU LD from the new tools, but.
In that case, why update your README?
Right.
Yeah, I mean, specifically, LOD has been getting better because Rui and Frank Song, the maintainer of LOD, are like good friends.
And also, I think Mold is getting slower as it supports more features.
It could be, but I think.
Sorry.
I know Rui gave a talk that I linked in my slides back in 2022, where he basically said a rule of thumb for how fast Mold is at linking is for every gigabyte of your output file, it takes 1 second.
Okay.
So he can link Chromium in 2 seconds.
Just for the record, I'm not saying don't use Mold.
Oh. Yeah.
I just think that graph doesn't look quite as good if it were to be.
Yes.
It says Clang 19.
Yeah, Clang 19's.
Oh, it does say LOD 19.
Oh, okay. Then I could be wrong.
Did he just forget to update the version number?
Probably.
He can make me stuff.
All right. There was a question over there. No. What's up?
Somebody maybe add some features.
The GOT and the PLT. Yes.
Okay. But what can you tell us more about like the types used? So I recall that when 64-bit architectures became available, more accessible, that a lot of people were saying that, oh, you're going to use twice as much memory, but it's more like maybe like GOT, like there's and PLTB, they might have some 64-bit types, but then a lot of the, let's say, entries or the indirect addressing is still, they're going to be smaller types. Is this something you come across? Or,
Yeah, so I think, where do we read? That's reading the dynamic table. This is doing the bloom filter that's inside the. Oh, why is this not in its own function? Anyway, where is do relocations? Look up system 5 symbol, look up GNU symbol.
How long is this file? Oh, never mind.
It's not that long. I blew it up massively. Where
is
do
long.
we do relocations?
540 minutes.
That's
Like, this whole live
at least 340 lines
like,
long.
this was written for SerenityOS, right?
Yes, and I wrote half of it. You can see my name on the files. It's my name up there.
We should have the Get Blame plugin so that we can see your name everywhere. There we go.
Are you interested in having Jason do a code review of this library? It's
No.
Also available
No.
for on-site training.
And time to wrap this up.
Sorry, guys.
At some point here, we look at all the relocations.
Like comments.
There's like a big old switch thing. Where'd it go?
Hey, I rarely say that.
Here we go. Why are we using it on this? Just to switch static into, okay.
I'm trying to get you business, Jason.
I'm gonna find a new meetup.
Yes, so for those
South
actual.
Denver, C++.
Katie needs to start that one. You still live down there?
Yeah.
64-bit file or link, is the program going to be twice as large?
No, the program won't be. Certain parts of it will use more memory. All your pointers will be bigger. But
Yeah.
I think.
But even the runtime, the address space.
Yeah, I mean, most of these relocations are still using 32-bit offsets, just because they assume that nothing is going to be 4 gigabytes away in an executable.
Right.
Yeah, I mean, another thing to keep in mind is that for things like ARM 32-bit versus ARM 64-bit, some of their instructions only have like a 24-bit operand or something like that. So in order to actually create large binaries for those platforms, you have to insert thunks at certain locations to trampoline yourself to the right location instead of being able to encode it directly in the instruction. I don't know how prevalent that is in ARM 64-bit, but I know in ARM 32-bit it's a really big constraint on the size of your application. So, things like that go away when you have a slightly larger instruction size that you can use. But I think for things like the GOT entries and PLT entries, gosh, I think I used to have some debug code in this when we were developing it that would actually dump out the entire GOT and PLT and whatever else. But for the most part, I think those are like 8 to 16 bytes per entry. Maybe the PLT is 24 bytes per entry, so like 3 pointers worth. So it's, unless you have thousands of external symbols you're calling from that library, it's not going to be a significant part of your ELF. So.
Follow up the gentleman's question earlier. Static linking, won't that theoretically always be faster?
It will certainly get rid of some of the overhead of having these tables.
Does it make a difference?
If you have all your, if you have the glibc and the tons of other libraries already in memory, then it will just page them all in.
Yes, something that you're
calls that Jason was talking about.
Yeah, something you're paying when you're using dynamic linking is some of that cache performance of things, because you're going to have your libraries loaded at completely different virtual offsets in memory.
It depends. What performance are you asking?
Exactly. Does it ever make a difference?
Yes.
Yes.
I mean, so.
But
are you? Yeah. It depends on. You're talking about runtime performance of the application, not of the linker.
Correct.
Then yes, it can have. It can be either. It can be worse or better depending on other things in your system.
Yeah.
Basically, it has to do with caching.
For a single application, your performance is always better. But if you have a cluster of applications,
But you never have one application on your machine.
yeah, for a cluster of
unless it's
applications,
embedded.
yeah.
No, we didn't have one application on the machine. We have one application per processor. So if you can pin
system or deep space mission or whatever.
if you can pin the application to a processor, like to a core, then you can get very significant difference.
Okay.
But it's probably not the low-hanging fruit.
Yeah.
So,
But do people actually pursue this?
yes.
Yes, in embedded, it's a very hot topic.
Extremely latency sensitive.
When you said deep space mission, I've never actually done aerospace, but I've had aerospace students.
Well, you have an aerospace.
And there's aerospace people, people who have actually sent rockets up are in this room. Statically linking all the things so that you know exactly what byte offset in the binary that thing is in case you need to patch the satellite after it's been launched is a thing too.
Okay, so the maintainability or
for that really niche specific case.
That can go both ways.
Yeah.
Yeah, for extreme latency sensitive things where you can actually measure the difference, it does make a difference. And actually, in SerenityOS, I made a change to statically link libmain. So there's a library called libmain that basically does nothing other than, it's very small. It does just
It provides the symbol main and calls a symbol called Serenity main with a nice argument list.
Yeah, it basically does some argument list mangling. And it was, I don't remember what the performance difference was, but it was huge. But you could, if you ran like a shell script just calling like tofu, and you did it 100,000 times, it would take like 10 seconds or something. After I changed it, it took like 100 of a second.
So they were talking about the process start time, not the like steady state runtime.
Right. Yeah. But that's what I mean. Like it depends on what performance you want to affect. Do you want to affect process start time? Do you want to affect the time, the function call time?
Called process cache efficiency. Yeah.
So
even
for a bash script versus a microservices thing. I mean, microservices live for a long time, but they take a while to start up. a bash script, they pop into existence and disappear all the time.
And even for function call time, you're only going to see this performance hit when you call a function from a different library.
Right.
So if you're sitting in your hot loop and you're calling the logger from liblogging, like, first of all, stop that. But also, like, that's probably not, it's not a hot loop if you're calling to some external library. Or like, so it's something you should be aware of with your performance critical
And
things.
you might not be able to detect it if the code is in instruction cache.
Right.
So it might be that you can't even detect it, depending on everything.
Yeah. If you have a really beefy computer and your thing is super high priority, then you're going to have a massive instruction cache and it might not matter.
Exactly. And the redirection is probably data cache, so that's probably, that indirect lookup is probably going to get optimized for the
Yeah.
So it is probably time to start practicing.
Yes. So, okay, my IDE is frozen, so no more demo.
Well, send in a call to JetBrains, I guess.
Yes.
Send it, Teams.
So I think that's, where did my talk go? I think that's all that I had. We had a lot of great discussion here, so. Everybody, what's up?
Macs?
No, I just have a really nice one. I bought this because we're building Ladybird for Mac OS, and so I really wanted a beefy Mac computer to help debug that.
Business expensive.
Oh yeah, no, that was mostly a joke. All right. Okay. Thanks
Questions at the bottom.
Yes. Questions. Thank you. Thank you very much.
Thank you.